Hello, everybody. Welcome to the first session. Sorry, welcome to the first session of ML Healthcare, and we are very excited to kick off this session. Primarily, we came up with the idea of ML of Healthcare because we didn't have it initially in Cohere, and we thought something that it was a really important topic in today's community, how it's growing, and the research that's happening within the ML Healthcare, right? I have my colleagues here with that is Lima. I have Omema, and we are trying to bridge this gap between Cohere within the ML community, and we have a lot of exciting events mapped up that we can go over later in our channel as well. So don't forget to join our channel as ML Healthcare on Discord. I'm going to quickly introduce our speakers. Today we have Ali. Ali is basically a third-year PhD candidate at Stanford Intelligence Laboratory, advised by Professor Serena. He is currently a research intern at Microsoft Research Health as well. His work primarily focuses on multimodal learning, multimodal retrieval, augmentation, agent-based systems, and basically emphasis on precision medicine. Min here is basically Min is a fifth-year PhD candidate at Stanford Laboratory as well, advised by Professor Serena. He is also a core member of Stanford community. He is also a data science scholar and has also worked as machine learning engineer at Hugging Face as well. He primarily works on statistical learning, vision language models to create open source models for people to use in the healthcare section. Thank you, Ali and Min, for taking out time for this session. They're going to basically present a paper called Biomedica that was accepted at CVPR 2025. Over to you, Ali.
Thank you. Thank you so much. Thank you for the great introduction. So yeah, we're really excited to be here. And before we start and we explain like our work on the Open Biomedical Image Caption Archive, I do want to acknowledge the amazing team, multidisciplinary team across statisticians, computer scientists, data scientists, clinicians, and wet lab scientists that make this work possible, and of course our advisors for guiding and providing all the feedback that was necessary to create this work. So let's go over the overview of the talk. And it's divided into 3 topics. So we're going to go over a motivation for scaling biomedical vision language models. Then we're going to talk about our work. And then we're going to share some perspectives of things we've seen after training multiple runs of our models with large-scale biomedical data. So let's start. So the first question, or like how I'd like to start, is just by asking a very simple question. How are medical large language models or vision language models generally developed? And if we look at the dataset perspective of how these models are developed, in reality, any like specialist models is actually constructed in the same way. We have a base model that is pre-trained on trillions of tokens, right? And this includes both the pre-training with SFT and then also reinforcement learning. But then after that, after we have our base model, we fine-tune this model with a specialized data set. Let's say in medicine, a 2.1 million token data set would be considered like quite good. But of course, the image I showed is not really the real perspective. Here I have an image in which 1 pixel corresponds to 1 million. And I promise you that there's a dot here. You just cannot see it. But I promise you that there's a dot here, and there's a perspective of 1 million compared against, versus 3 million. 3 trillion. And it's a huge difference, right? So it's not surprising to see that, early on I worked with large language models and was able to characterize a similar gap, though not systematically, but with some tasks. And I was able to see that basically the base models would actually perform better than the medical fine-tuned models when evaluated, of course, in real clinical tasks, right? Such as Metaline, a paper published last year. And more recently, we've also seen that behavior in other tasks we've proposed, such as, for instance, matching the conclusions of systematic reviews, medical systematic reviews. And here we see, again, there's a lot of things going on here. The only thing you need to focus is on this arrow, which shows the trajectory of accuracy of the base model compared to its fine-tuned medical model. And you can see that there's a degradation in performance. And of course, we saw this in multiple tasks that we evaluated our models, but there's a more recent study by CMU that has observed like a similar trend across a lot of models and across a lot of tasks. I really recommend reading this paper. And it really shows that there's a limited impact on this medical adapted LLMs and VLMs, right? So yeah, basically medically fine-tuned models do not generalize as well as their counterparts. And when you think about it, it is a data size problem, right? Because like you might have, for instance, histopathology data, but it might be only from one hospital. And if that's the case, you only have one scanner. And we know, like, instance for microscopy, specifically for histopathology, different technologies make the tissue look extremely different, right? It's super noticeable by the human eye, right? So it's definitely a batch effect. So if we take a step back and we reflect on why this is a systematic issue with the models that we've developed as a community, we can go back to, for instance, scaling laws, and we see that in order to get really good models, you need to scale across multiple axes. And these are not per se orthogonal, but let's just say they're orthogonal for now. But you need to scale across compute, parameters, and data size, right? And this is something that as a community we've definitely tried to accomplish, like compute. There's been amazing papers on the medical community in which people have tried to use more compute to scale a model. We've also fine-tuned models that have 7 billion parameters, 20 million parameters, 32. So it's not a problem about compute or a problem about parameters. But I think the most important part in order to make this work is also scaling the data size. And when I mean scaling, I'm not only saying like, get a data set from one hospital, right, of like 2 diseases and collect like 1 million data points, right? Like I also mean diversity and more importantly, frequency of those of the data. There's also like a very important paper published last year called No Zero Shot Without Exponential Data, in which they revisited the so-called zero shot capabilities of CLIP, and they found a log linear relationship between the constant frequency and CLIP's zero shot performance. So for instance, zero shot classification and retrieval. And I mean, there's a lot of stuff is going on here, but the only thing you really need to do is just go to one plot and just see that the pre-training concept is increasing exponentially, but the performance, or in terms of accuracy, is just improving linearly, right? So we really need a scale and diverse data in order to train such medical models. And of course, in the community, in the general domain, there's been amazing efforts to bring this to the community, such as Lion 5B, and we've seen a lot of amazing models that have been built with public data. But when it comes to the biomedical side of things, we're definitely behind. So the question is, if we need large scale and diverse data, that's of course something that we think we need. But where can we find such data that covers the landscape of biomedicine? And the answer is, of course, or one of the answers. I don't think this is the only source that we can leverage. Is that we can use scientific articles, and we're not the first lab to leverage scientific articles. This has been leveraged by a lot of labs before. And the reason why they've used this type of information is because scientific articles are rich multimodal data. They contain textual information, images, captions for those images, and they also compare and contrast those images in inline references. Right, so there's a lot of things we can exploit from this data source. And in particular, I cannot talk about scientific data without talking about PubMed, which offers this data at scale, and it also offers like a server in order to retrieve this data. Right? Of course, not all of PubMed, but of course only the open source section of PubMed. And in particular, PubMed is growing exponentially too. This is up to 2017, but you can see that the number of publications that have been indexed in PubMed has grown drastically. And I think this number is from 2023 or 2024, but like at least in 2023, there were 1.5 million new articles that were indexed in PubMed. And the good thing is that changes in policy, for instance, not only the US, but in the world, I think will make it so that there's more data available as open source. Because, for instance, in the US, all NIH-funded research has to be publicly accessible for everyone. Great. So this has been some motivation to scale our biomedical vision language models. Now I'm going to pass it to Min so he explains more in depth the biomedical image caption archive.
Great. Thanks, Alejandro. So I think Alejandro set us up really well, kind of motivating why we need a data set like Biomedica. And so let's do a deep dive into how we went about building it, as well as some of the applications that were enabled by Biomedica. And so this is a bird's eye view of the data pipeline, where we start from PubMed Central, where the raw files exist, and we extract 6 million articles worth of data. And so from there, we get 24 million image caption pairs and associated metadata. We do some additional preprocessing and transformation for quality for the images, and ultimately we have it uploaded to Hugging Face. Now, something that we really wanted this to be was for users, for Biomedica to be really accessible. So for the user's perspective, it should really look like this, right? Biomedica ETL, so black box, what they care about is the way they interface just through Hugging Face and able to access data easily. Okay. So we spent quite a bit of time thinking about what type of data do we want to include beyond just the image caption pairs. And so we tried to be very comprehensive about the associated metadata that we can put into our data set. So when I say metadata, some of the examples include unique IDs associated with the article, things like title, abstract, citation, as well as things like publication date, licensing information. And we did this for all 24 million image caption pairs that we uploaded. And one of the main reasons why we wanted to do this was so that we allow users to really choose themselves what they want to include when they generate their data, make sure when they're using this data for downstream applications. We also did additional work to the images. So we efficiently annotated all 24 million images. And so with concept labels. And so this is important because one thing Alejandro actually mentioned during the motivation was the paper knows there is shot performance without exponential data. And so concept frequency matters a lot when we're training these models at scale. Right? We want concept diversity. And so in order to do that, in order to know what type of concepts are represented in the data, we actually do need these concept labels. And not only that, these labels allow us to filter the data to specific domains of interest and also balance the different type of concepts when we're thinking about the data composition. And we actually took a pretty simple approach to doing this tagging. And the way we did this was we passed the images through DynoV2, got these DynoV2 features, projected down to principal component space, and did clustering. And so rather than annotating individual all 24 million images, we instead annotated the clusters. And we had PhD researchers who have wet lab experience as well as clinicians actually label and annotate these clusters. And so when we have new images, all we have to do is project down to this space, this cluster, and we can propagate the label that way. And so this is the result of the concept labeling that we did. And so each row here represents a unique cluster. And as you can see by each row, like you can really see like specific good delineation of concepts. So we see like radiology images, we have microscopy, and then you start seeing things like plots, things like pie charts, bar plots. And so you can see, despite it being a very simple approach, we took this more traditional supervised learning approach that was supposed to be fast. We're able to get these clean clusters for our images. And so now that we have these concept labels, we're actually able to dig into the composition of this data set, Biomedica, and kind of glean upon some interesting insight. So for one, a lot of the images contained in our data set are multi-panel. So these are figures that have sub-figures within the figure. So it'll be like figure A, figure B. And what's interesting is, for instance, the caption might mention things about both and make comparisons between both sub-figures. And so that's something unique about the images in Biomedica. Also, we're able to kind of look at what type of concepts are represented. And interestingly, more than 50% of the 24 million images are plots and charts. I think that somewhat makes sense in that plots and charts are a very common way to summarize and share scientific results. So that's not surprising. We also do see a lot of biomedically relevant imaging modalities like microscopy, clinical imaging like radiology, immunoassays and such. And another thing to note is here I'm showing more of a global high-level taxonomy concept, but we also have fine-grained labels where, for instance, for microscopy, we can look at things like confocal, light microscopy, electron microscopy, not just this global microscopy label. So just because the data is open source, that doesn't mean it's accessible or easy to use, especially at the scale of Biomedica. It's such a large data set, and we really wanted to think about making it accessible for the users. So I think we've mentioned this multiple times, but the Biomedica data set is, for one, available on Hugging Face, and so it's integrated into compatible with the datasets package. So it's really easy to download the data with just a few lines of code. But I think the more interesting part is this capability of streaming. And so Biomedica as a whole is worth like 30 terabytes of storage. So that's not trivial, that's quite large. And so we actually made it a challenge for ourselves to train on a compute node with much more constrained storage. So only just 50 gigabytes of local storage, which means obviously we can't download all 30 terabytes worth of data on a local disk. But because we had this streaming feature, we were able to train on all 30 terabytes worth of data, despite this kind of challenge we put ourselves against of constraining the storage space. And kind of in that lines of accessibility, we also want to think about building these subsets that could be useful for the community. And what I mean by this is, rather than needing to download all 24 million images and need to filter for the images you want, we actually made these subsets available for Biomedica, such for instance, like microscopy or clinical imaging, so that the user can directly go to that subset if they only want to use that set of images, say, to train a specialist model. Okay, so I spent quite a bit of time talking about how we built the data pipeline, as well as some of the toolings around it, like filtering and streaming. But I also want to talk about some of the applications that were enabled by having built out this data, as well as some of these toolings. So for first application was training a CLIP model. And so we continually pre-trained a CLIP model on our Biomedica data. And we actually took a couple of different strategies when we were designing our training mixtures. And again, this was enabled by the fact that we had these concept labels that we generated for all 24 million image caption pairs. And so the first strategy was to do no filter, right? What if we trained on all 24 million image caption pairs? The second strategy was data balancing. So here we actually looked at the data composition and we wanted to balance the concepts representing different domains. And lastly, we tried concept filtering, where we filtered down to image caption pairs that are more biomedically relevant, right? So microscopy, clinical imaging, and such. And so that was like the smallest set of just 6 million image caption pairs. And interestingly, doing all that, to the right, what I'm showing is zero-shot classification performance across 6 different biomedical domains. So these are averages across tasks that belong to these domains. And we see that concept filtering and balancing really help a lot. And so our best performing models that achieve state-of-the-art performance across these domains are the models that went through this training strategy. And we were actually able to outperform prior CLIP models that were trained with similar scientific literature-based data, like BioMedClip and PMC Clip. And so what I'm showing you here is the table of all the evaluation zero-shot classification tasks that was used to summarize or show that built that radial plot that I showed in the previous slide. But I think one of the points that we want to make here is, again, and Alejandro alluded to this, but evaluating our models across the wide span of biomedicine, not just looking at pathology or radiology in these narrow domains, but again, assessing the capability of these models across these domains. And next slide. So yeah, when we look at our family of Biomedica CLIP models, we actually outperform on average across all these biomedical domains compared to the prior models. And so if you take a deeper dive, so these are some of the zero-shot classification benchmarks we're looking at. The blue and green here are models, our models, so a family of Biomedica CLIP models, compared against BioMedClip and MedSiglip. And MedSiglip actually is a model that just came out like a month ago as part of the MedGemma technical report release. And interestingly, our models that were only trained on scientific literature data are still able to outperform MedSiglip, for instance, across all these different domains. Next slide. Another experiment we did is we play around a lot with batch size during training. And so if you do contrastive learning, you'd be familiar with the fact that batch size matters a lot because of the number of negative examples you want to show during training. And so we tried this experiment during training where when continually pre-training on Biomedica data, we trained with a batch size of 8,000 versus 32,000, and 32,000 is closer to what CLIP was actually trained with, the actual batch size. And we noticed an interesting phenomenon. So the top plot is the training loss curves of the two models, where blue represents the bigger batch size training, and then the green smaller batch size of 8,000. We see that the bigger batch size allows for faster convergence. And not only that, later in the epochs in training, we start seeing the curve be more stable compared to using smaller number of batch sizes. Furthermore, at the bottom, we're seeing more zero-shot classification performance across biomedical tasks. Scaling batch size does help in performance in this way, although there are some notable variations. And I think something we've noticed also is there's a lot of variation across epochs in training. And so we actually released all the checkpoints so that the community can choose to use any of these models at different epochs and also do further analysis why we see some of these interesting phenomena. So moving on from embedding models, second application, autoregressive VLM. We took Hugging Face's open source small VLM model, and we fine-tuned it further to Biomedica data. And of course, we had to convert the captions into instruction tuning style data. And so as an example, like this kind of image VQA style format on the left, as shown about microscopy, image understanding. And so doing so, we were able to show that a model like small VLM can perform quite well on closed VQA tasks, on common medical VQA tasks. And thirdly, we built out the Biomedica index with the goal of enabling RAG capabilities from Biomedica. And so if the user provides a question, that question is converted into a structured query that matches the index. And from the index, we retrieve the top K most relevant full text articles. Those are further summarized and provided to the LLM so that the LLM can synthesize an evidence-grounded answer from scientific literature. And so, yeah, so Biomedica, building Biomedica has really enabled us to train CLIP model, autoregressive VLM, and also build out an index that allows RAG. And so, yeah, and not only that, we see strong performance across all these applications. So Biomedica seems to be quite a useful resource. Another interesting thing we noticed working with Biomedica is the size of the captions. And so the captions that are associated with the images tend to be quite long and exceed beyond 77 tokens. And 77 tokens, you might ask why this number. This comes from the max context length of typically used for training CLIP models. But by limiting yourself to 77 tokens, we're really limiting ourselves, right? We're not capturing the full length of the captions. And so we actually, during training, extended this context length in different amounts. And we actually see a much stronger performance when we look at real-world retrieval tasks like retrieving radiology images, radiology report, where the report tends to have text that goes way beyond 77 tokens. It's typically 100 to 500 tokens long. And in these cases, increasing this context length during training really helped us a lot. Right. So with that, I'm going to pass it back to Alejandro, who's going to be talking about some perspectives, lessons learned, and things like that from having worked on Biomedica.
Thanks, Min. So one of the things that I want to mention, and this is like some of the things I've discussed with colleagues, and they seem to agree that the field is definitely evolving, and has been evolving over the years, right? Like at the beginning, or not so long ago, people were really interested in like the algorithms, right? After that, the deep learning era came, and the interest was in making deep neural networks deeper. But when we're talking about foundation models, there's definitely an emphasis, of course, in infrastructure and make them fast. There's a lot of engineering involved. But one of the most fundamental pieces to make foundation models work is scaling data, right? And doing the engineering to obtain that data. And we realized that while making Biomedica, right, like tweaking the laws, wouldn't, or like using like different models, like wouldn't give you such boost in performance as much as having large scale data. Having said that, I want to go back to one of the first images that I shared at the beginning, and I promise there's a pixel there over here. But even though we went through a lot of engineering to make Biomedica possible, there's also an image to scale. Like Biomedica is still not a very large data set compared to what we use in the general domain. And this is one of the limitations that we have with healthcare data, right? So having said that, I would like to share some hot takes, or probably not so hot takes, based on the things that we learned while creating Biomedica. So the first one, and it might be obvious, but the first one is like, to measure is to know, and if you cannot measure it, you cannot improve it. There's a really famous quote, right? So one of the things I noticed early on when trying to design our benchmarks was that they were really noisy. I'll show like an example here, which is a tile from a histology section, right? So it's a very, like, let's say a crop of some large area of a tissue. And the question is, and this is not per se the exact question, but it's like of the same flavor. But the question is like, which organ system is normal? And the answer is brain. And well, there's a lot of things wrong with this question, but I mean, I'm just gonna go to the most obvious one, and that is like the question is asking about the organ system, and what we have is a patch of a tissue, and there's different levels of organization, right? We have cells, we have tissue, we have organs, we have organ systems. So the question is orders of magnitude of, right? And there's a problem that has been highlighted by a lot of people before, but I think it's definitely a problem that we definitely have. So that's why, for instance, in Biomedica, one of the things we did was we collected 60 benchmarks across different domains, and we asked clinicians and wet lab scientists to actually look at the quality of the images and the tasks, and first of all, see how noisy they were. And we had a filter to just make sure that we had good data sets that were deemed relevant by these experts in their fields. And that really helped us a lot to iterate and really see some signal. The other thing that we observed is also, and in the Biomedica paper, we go over it in the prior work, and that is like the way these systems the way clip models were evaluated in medicine was by taking the encoder, and then you would train a decoder to evaluate on OpenVQA tasks. And the problem is like those decoders used to be, or are usually like large, like transformers. So there's a lot that is being learned in that transformer, right? And of course, there wasn't a standardization. So when you're trying to compare methods, like method 1 against method 2, you really didn't know if the performance gain was because of the encoder or because of the decoder, right? So that was definitely a problem. And of course, that's why we decided to do zero shot. And when we did zero shot, we saw that, for instance, previous work, even though the decoder approach to evaluate the models didn't show a big gap between them, with zero shot, there was a tremendous gap of at least an average of 20% accuracy, right? Which was not really reflected. So in the previous evaluation approach. So TLDR, evaluation is really important, and we just should make sure that these are not as noisy, and we should also make sure that the evaluation regime we're using is actually adequate to actually see the signal we want to see. So it just boils down to, if you don't trust your measurement, how can you improve your system? And then another thing, and I think this is the thing that worries me the most, is because we're doing things at large scale, it's really hard to have a auto distribution test set. In Biomedica, we did run the image hashes of the entire data sets that we use for evaluation in our pre-training data sets, and we saw that there's no collision. And also, as Min mentioned, most of our data is also multi-panel. So you can argue that there's definitely like a different distribution. But and this is probably not a problem with clip models, but with autoregressive models, what I'm seeing more and more these days is that they get like a new model is released is like really impressive in terms of performance, but the way the model was trained was just collecting a lot of data sets and getting the training set and the test set, and then you train on the train set and evaluate on the test set, as like normal machine learning practitioners would do. The problem is like that approach doesn't really tell you. I mean, that's okay. We should do that, but we should still get evaluation benchmarks that are out of distribution, because of course we will always encounter them in practice and when we deploy them. And I didn't mention this at the beginning, but this is such a huge problem because, for instance, in any modality you can think of, different devices that are used to acquire the modality will apply different batch effects. And there's also, I was reading a paper actually this morning on this study that they saw, like, look, all these VLMs are really good with these devices, but when you look for other devices, you see that they really didn't learn the morphology. They learned the batch effect, so they're not really generalizing really well. So that's something that to keep in mind. So I hope that as we progress as a field, we of course accept in distribution and take these words with a grain of salt, because like what is really in distribution nowadays, but like out of distribution, but we should have in distribution and something similar to auto distribution test set to provide some numbers in our papers and have real progress in the field. And with that, I have 3 open questions that I'd like to share with the community. I'm not really sure of the answer for these questions, but I hope as a community we can explore these questions and progress and bring progress to the open source community. So the first one is regarding like the data or the scaling of biomedical AI, and the question is, like, we as a community, have we really untapped everything we can untap from this data? And there's of course, like, people have explored medical Twitter as a source, PubMed as a source, but I'm pretty sure there's other sources that we can exploit in order to scale vision language models. As an example, in the Biomedica paper, we also have another source that we use in order to create a test set, and that is Flickr. So we use medical Flickr, only the open source subset, so questions that clinicians allowed redistribution. And what we do with that is that clinicians, some clinicians upload de-identified images to Flickr with some descriptions of things they're seeing on the histopathology images, radiology images, and we use that to create a small data set. But of course, once we really untap the full potential of biomedical AI, we're gonna hit the limitation of scaling, right? Like this, we've seen that this is seems to be a problem in the general domain. So when that happens to medicine, which I think is not yet there, but when that happens to us, like, how are we gonna keep scaling? Like, are we gonna try synthetic augmentations, or what are the approaches that we're gonna use? And the last question is, and this is not regarding the data, this is regarding like the method on how we create these models, is how are we gonna get the best model, the most robust model, the most robust VLM? Is it gonna be through medical post-training, or is it gonna be related to, just, pre-train everything from the beginning with all this medical data alongside reasoning data, like mathematical data, physics data, and so on, right? And before I go into the QA session, I'd like to just, again, acknowledge everyone that made this work possible. And of course, first I'd like to acknowledge our um, funding sources such as the Stanford Data Science, Merlot, the High Institute, of course, Marvel, which is the lab run by Serena Yeung-Levy, and of course, NVIDIA and Amazon Web Services for providing extra compute resources. In terms of our external collaborators, I'd like to thank Hugging Face and NVIDIA for both helping us with the original Biomedica paper and also the extensions. And of course, our advisors and the main Biomedica team again. Great. So without, so this has been our talk. And if there are any questions, please feel free to ask them.
Yeah, thank you so much, Alejandro. This was a very interesting presentation. Yeah, if anyone has any questions, please put them in the chat. There's a question. Okay, so with regards to scaling data, do you think biomedical AI can be used to create synthetic data? What are the other ways to scale data?
So I didn't quite catch that question. So biomedical AI is what, sorry?
Sorry, so with regards to scaling the data, what do you think about biomedical AI can be used to create synthetic data, and what are the other ways to scale the data?
Oh, I see. Yeah. Okay. Great. Yeah, that is a great question. I think synthetic data is definitely an approach. I just think that the reason why we need to scale, like concept frequency, as I mentioned before, is really important, right? So the issue with when you generate synthetic data, right, and you only, for instance, imagine you're trying to create synthetic data and you only have data from one device. Let's say you're in CT scan and you have a Philips device, right? But there's Siemens and other companies, right? And they really have different batch effects, right? So you create more data, right? With this one distribution, right? And the only thing you really accomplish is to create this batch effect, right? So when it's deployed and it's deployed to a different hospital that doesn't have the same device, right? Then you are in big trouble. So synthetic data generation, I think, is a possible avenue, and there's really interesting work around that area. I do feel that we do have to be cautious on how we do synthetic data. So there's pre-foundation model work, for instance, in microscopy and histopathology, in which they learn the different distributions or different batch effects from different microscopy devices, scanning devices, and they use that to provide augmentations. And they're very realistic, right? And it helped their machine learning algorithm. So probably something along those areas of learning those batch effects, right? It's really important. Like augmenting the samples with those batch effects would be really, I think, would be an interesting direction to explore.
Yeah, go ahead. Sorry, I was going to add something after.
No, go ahead.
Yeah, I was just going to say, like, I totally agree with Alejandro. Like, batch effect generally is like a big problem in like biomedicine and all that. But I would say synthetic data could be useful in also more like post-training in terms of like having your model be able to answer like visual question answering in a specific format and things like that. And so, for instance, like LavaMed, and we also kind of alluded to small VLM fine-tuning to data with visual question answering, right? So that it can actually learn to answer questions. So things like that, I think it's quite useful, and you want to use this type of synthetic data to be able to scale.
Yeah, and also it's more challenging because medical data and images are so heterogeneous, and it's so difficult to capture the biology of it. Like every, like domain of histopathology or radiology, they're all like so different, and the minute subtle details are so difficult to even capture this in synthetic. But yeah, that's very challenging.
Exactly.
Yeah. Emmanuel,
I do
you
have
want
a
to
question. Oh, sorry.
Yeah, thank you. I already sent a message to the group. Thank you very much, Alejandro, for your presentation. Awesome work you guys have done so far. I just wanted to know if other sources were considered, like Scopus, Web of Science, Google Scholar, while I noticed only PubMed was there. So that's like a question.
Yeah, that's a fantastic question. Yeah, so PubMed, there's an overlap of what PubMed indexes and all these other sources index. Before us, there's also a paper that used Nature, like only Nature publications. They have like a service you can use, but we found that there was a huge overlap when with all these different sources, right? So we stayed with PubMed. Um, the other thing is that you can always access a paper through the internet, right, with PubMed, but not everything allows redistribution, right? Or like normally like redistribution or like training with the data. So you have to be really careful with that. So that's why like PubMed has PubMed OA section of PubMed, and we particularly focus on that section. So there's also like another limitation for scaling. Like we need to focus on things that we can actually use for training, right? So yeah, that's one of the considerations. And similarly, for instance, for Flickr, as I mentioned before, Flickr has lots and lots, like orders of magnitude more medical images than the ones that we use for our test data. However, only a small subset have explicitly added a redistribution license. So yeah, we only limit ourselves to those.
Thank you.
Mhm.
Maybe do you had a question, right?
Yes.
Mhm.
Thank you so much actually for the presentation, and thank you for accepting the, um, the invitation. I have a question about the limitations, because I would love to know more about these limitations, and as it's an open source data set, so I think you are open so that the community can collaborate on this. So for
Mhm.
example, based on these limitations, how can the community elaborate on this? So if we have anyone here can want to contribute, uh, he or she can contribute on that.
Yeah. Thank you so much. Yeah, that is such a yeah. The community is like an amazing component of Biomedica. As Min mentioned, like the Biomedica subsets are actually something that were requested by the community, right? Like we didn't um well we promised we were going to release some, but then we released some and then people are like, hey, like I'm really interested in this subset, could you please like provide it? And yeah, we were doing that. So everyone can help with identifying subsets that they're interested in, and we can definitely serialize them. And there's definitely Biomedica has lots of limitations. So let me share a few of them. And actually, people have already tackled some of those limitations. So I'm really happy that people have already leveraged Biomedica to identify those. So I'll explain some of the limitations that haven't already been addressed, and then maybe talked about other ones. So the first limitation is that there's multi-panel images, and there's a caption that has information about those multi-panel images, right? So of course, for clip models, you'll like to have single panel and just a subsequent caption. So someone has already used Biomedica and has created a data set in which they only have single panel images. They decompose a single panel. I think, if I remember correctly, they did not resolve the caption attribution. So it has the general caption. So that is still a problem. So having decomposing the image into image caption pairs that are of the single panel resolution. So that's one limitation. And there's already some evidence that really improves performance drastically, of course, because it brings the distribution of the image closer to the evaluation that you're interested, like single panel images. So that is definitely something the community can keep on exploring. I don't think like we are done on that line of research. Another thing that it's really important is how to create VQA pairs from this scientific data. So this is something that we've actually been exploring for a long time, and we do have some data sets, and we want to make them available as soon as possible. It's just like, what are the best approaches? Are like, there's a lot of pipelines that can be created. So like, we just want to make sure that we give the best possible data to the community. And the other thing, of course, as already mentioned, is these models have a limitation of the context length they have. So extending the context length. were going to release a preprint really soon on how we did this via the pre-training, just having like a longer context. But of course, you can also explore approaches to have larger context lengths. So in summarizing all these things that I mentioned, like there's a lot of things that need to be done, and we definitely do not have the bandwidth to do all of those things with Biomedica. So, if everyone is interested in collaborating, or, you can collaborate to the Biomedica repo, or you can actually reach to us. And if you have any questions, we can help you either get started with the data, or, anything you like in terms of serialization, we can help with that too.
Yeah, and just to add, I totally agree with Alejandro. Another thing I just want to kind of mention is the fact that this data set is growing, right? Like we've mentioned, 1.5 million articles getting indexed every year. So we also do plan on doing an update of the Biomedica dump so that we have more. And so if the community can continue engaging with the data set using and letting us know like what they notice and what they want, I think that would be really, really nice as well.
Yeah. Maybe me and my colleagues, we can think about this, and maybe we can just have an announcement on our community so people can continue collaborating with you, because it's such a nice project. And as Mino said, we have papers each year, so it should be ongoing contribution.
Exactly. Yeah. And there's a reason. This is like the name of the project is really intentional. It's not called like the PubMed archive, right? It's called the Biomedica archive. And that's because, as I mentioned before, we have PubMed, and we also got Biomed Flickr. But internally, we actually try a lot of sources. We just end up releasing these sources because those were the ones that we used to scale. But yeah, like ideally, we really hope that we have a biomedical archive that really spans all the sources on the internet, that allow redistribution, that are open source, and that can really help the community to just, I don't need to reserialize all this data. I can just use this data set as, for instance, Lion, and I can just use this data set and explore different things such as data balancing, data filtering, whatever approach you want to try, creating like better fine-grained detail embeddings. There's a lot of things that the community can explore, but the limiting bottleneck for all that in biomedicine is data. So we really want to fix this problem first, and we would be really happy if people can build with this and explore different questions.
Yeah, thank you.
Mm-hmm.
Do anyone have any questions? Okay, if not, I have a question. So,
Mm-hmm.
so you mentioned about concept labeling, right? So it's involving the majority voting system. So, in case of inter-annotator disagreement, what specific reevaluation processes that I'm taking, and are there any plans involved to involve more annotators, or like develop more sophisticated consensus mechanism for future iterations?
Yeah. That's a great question. You know what? I think, of course, like our clusters are not, free of error, or like they have some error rates. You'd be surprised on how good the clusters are. Actually, like we went over this actually a lot of times because we thought there was a bug or something, because like it really is really it was a really strong technique to do the annotation. And we did, for the rebuttal process, we did add a inter-annotator disagreement on the clusters, and it was actually quite high in terms of the general concept, right? Of course, there's like the annotation is like from general to fine-grained. At least in the general, at least everyone agrees that when they're given the image and the cluster is like image light microscopy, everyone agrees that it's light microscopy, right? Like there's no question about that. In terms of the subdomain, yeah, that's a little bit harder, of course, and I think that's a limitation of DynaV2. The method, I think we are thinking of using DynaV3 to like rerun this experiment. It's an expensive experiment because like it does require like some clinicians and wet lab scientists to do the annotations. But yeah, definitely I think the most integral part that enabled a lot of applications for Biomedica was this part of the pipeline, right? So yeah, definitely, like if there's like other ways we can annotate the data, I think someone mentioned like, oh, why not using vision language models? We tried using vision language models actually, but the results actually weren't as good as this method. And of course, there's a paper by our colleague in our lab that explores like why VLMs are really bad at classification, right? So it's related to that avenue of research. But yeah, any type of method, we next iterations of the data set, as mentioned, we're going to release this every year. We do expect to improve different areas of the pipeline, and of course, the labeling is one of the things we want to improve. But there is high inner annotator within the clusters.
Sure. Yeah. I also saw that there was like good amount of improvement in procedure shot classification. I've seen in dermatology and in ophthalmology. So, what are the immediate next steps, or like validation processes envisioned to transition these like really impressive capabilities into practical and real world clinical research goals?
Yeah, that's good. I think you got it right. Like that's exactly what we should do. Like doing the evaluation of real world. I think at least in academia, there's definitely like a gap. In industry, you do see that there's a lot of work on evaluating the systems in deployed scenarios, right? And I think, and of course, in academia, there's been like small trials using foundation models in the clinic. Like I would like to highlight the work by Jonathan Chen at Stanford, who's done an amazing work over the years on deploying the systems in small clinical trials and see how these models perform. And usually, you see they always underperform, or sometimes they perform better than clinicians. It really depends on the task. So yeah, I agree. Like we should definitely, or like we should strive to move on from these evaluations and evaluate deploy scenarios. I think at least for academia and for the open source community, that's probably a little bit hard. So I think there's still like something we need to exploit. So I would say like these are like the current frameworks that we have, and we have for evaluation, we have 60 benchmarks. We have the clinic, and this would be the the gold standard. But I think like there's still a middleman or like a middle step that we have to explain as a community, and that is we need to also scale our evaluations, right? And we do this by just collecting multiple sources across different hospitals, across different parts of the world, and just evaluating how the model really performs in that stage, right?
I was just gonna quickly add something. I think Lima, you mentioned like you're referring the radial plot, right, with like the different domains and performance there for zero shot classification. So another I think avenue of improvement there is like better fine-grained perception understanding. Yeah. And then maybe this could be through the data, or maybe like the training paradigm or the vision encoder that we use. But that's certainly, and I think you mentioned this earlier, right? Like the images, right? The fine-grained information really matters when it comes to these biomedical images. And so that's probably another limitation that we're seeing, which is why the zero-shot classification, like if you look at the overall numbers, it's quite low. Even though we say we achieve the best performance, it's still low, right?
Yeah,
so
we still have a long way.
Another avenue to think about, just to add to Alejandro's points.
For sure, yeah. I think this is a start. I think there's a long way to go, but it's great that it's a start. Someone is starting right away, so it's great.
Yeah, for sure. There needs to be a lot of work in the evaluation domain in order to keep the progress in the model, right? And again, it goes back to like you cannot really improve what you cannot measure.
For sure, I totally agree with that. All right. I don't have any more questions. If anyone has any questions, I think. Oh yeah, there's one question here. So from a more holistic point of view, it should be that EHR or facts data should also be included to bring it closer to a real world clinical application. As you mentioned, the whole project is open source as well as modularized into subsets for more ease of use, where open source EHR and facts datasets considered to be included in the dataset. or is that an avenue to improve on?
So sorry, I'm having issues with my speaker.
Oh, okay.
So you said that, like, was the question like? Can you
So-
repeat just the question? Yeah.
Yeah, so the question is about
I would repeat it because I think you have a small problem with your microphone, Dima. Do you
okay.
mind if I
Yeah, go ahead.
use it? Okay. So they said from a more holistic point of view, it should be EHR or PACS data should also be included to bring it closer to real-world clinical application. As you mentioned, the whole project is open source as well, modularized into subsets for more ease of use. We're open source EHR and PACS datasets considered to be included into datasets, or is that an avenue to improve on?
Oh, thank you so much. Yeah, that is a really good question. Um, yeah, so EHR data is the gold standard that we should attain, right? Because like that's actually what clinicians use in order to deliver healthcare to patients, right? The problem with EHR data is that redistribution is a little bit harder, right? It's not impossible. It's just a little bit harder. So before this, I worked on a project in which we released the largest EHR dataset, like full EHR dataset that exists in the world, and I think it's still the largest. And when I mean EHR, I mean like not sections of the EHR, like the whole EHR, but all the sections of the EHR, right? And the largest we could do was 1,000 records, and it took like 2 years to do the release of that. So basically, like half of my PhD to release it. So I'm a little bit skeptical of really scaling EHR. At least, like people have scaled. There's and Microsoft Health Futures and Epic recently released a model with EHR. So I think make like if you work with providers of the technology, is definitely possible to access that data. It's definitely harder to give access to that data to more people, right? And if you've worked with EHR data, you know that there's a lot of limitations. Also, like a lot of times, you work with EHR data, you only can work with like a specific cluster, right? Like that it has like a lot of IP addresses blocked. You can only access it via like a certain provider. It really complicates things. So the good thing about scientific data is that there's a lot of images that were de-identified, right? That come from case reports, for instance. And they are clinical images. They are indeed clinical images that can be shared and can be redistributed, but have already gone through the problem of de-identifying images, right? So it really, I think definitely we should scale EHR data, but in order to get there, there's 1 million things that have to be solved first. And I think, we should try to give the community something before we get there. But yeah, that should be the gold standard EHR.
All right. I don't think there are
think we
more
should wrap up.
questions.
I think we should wrap up because we
Yeah.
are already.
Yeah, there's already 20 hours. Yeah, thank you so
Yeah.
much, Alejandro and Min. Yeah, it was great. Thank you so much for taking time to share this work. It's such an inspiration for all of us to work, and there's a lot more to work on. So yeah, thank you so much. Have a good weekend.
Yeah, thank you for the invitation. Yeah, thanks.
Thank you for having us. Yeah,
Yes.
pleasure.
Thank you so much,
Thank you.
and take care.
Yeah, okay, bye-bye.